2019 question 4. Based on the looks of this, it's dealing with majority related rates. Okay, with a little bit of separable equations, so it's a little bit of everything. Okay, so we have this barrel. It's a cylindrical barrel. Okay, with a diameter of 2 feet. Okay, we know that the water drains out through a valve at the bottom. They don't show what that valve is, but water is leaving. Okay, the rate of change of the height with respect to time. So they give us an equation here. And they also tell us that the volume of a cylinder with the radius r, height h, is v equals pi r squared h. Okay, here we go. Find the rate of change. Find the rate of change of the volume of water in the barrel with respect to time. Okay, so right away, I see the rate of change. So that's d of something over dt. Well, what are we finding the rate of? We're finding the rate of volume. So we need to find dv dt. Okay? Specifically when h is 4 feet. Okay? So here's what I'm talking about in terms of this last part here, indicate units of measure. Let's say you guys had no idea how to do this problem, right? We know at the very least that we need to find dv dt. Well, how do you measure v, volume, right? We know it has to be cubic units. So in this case, it has to be cubic feet. Now, what time measurement did they use here? So if you skim through this, what time did they use? They used seconds. So this is going to be cubic feet per second. Even if you don't know how to do the problem, you will get a point for units there. 9 times out of 10. Okay? So here we go. We have V equals pi r squared times h. Okay? So this one is tricky, all right? Because of the shape of our barrel here. I want you guys to really think about this. R stands for the radius. H is the height. And V is the volume. Okay? Now the thing is, we're going to take the derivative of this. So the derivative of V, or the differential, is going to be dV. What you guys have to know is that since this is a cylindrical barrel, right? The radius is not changing. What's another word for not changing, right? We know that the radius here is constant. Okay? So knowing that the radius isn't changing, it's constant, you have to treat r like it's a number. Okay? So when you're taking the derivative of this here, there's no need for a product rule. And that's where it got most of the students last year. Okay? So really the derivative of this is really just pi r squared, because that's a constant. And the derivative of h is really just 1 dh. Now, if it was any other shape, then you would have to use the product rule here, okay? So just keep that in mind. So let's keep going. So we want to divide our differentials by dt. And we want to find dv dt. It's ready by itself, so we just need to plug and chug a little bit, okay? So do I know what dh dt is at 4 feet? Well, they give me the equation right there, right? So if I plug in 4 feet for h, that's just negative 1/10 times the square root of 4. Negative 1/10 times the square root of 4. Now, what's the radius, right? Well, if I know the diameter is 2 feet, the radius is always going to be 1 foot. So that's just pi 1 squared. Okay? I don't need to put in units because I already got that. Okay? I'm going to leave it here. Equal is equal. Okay? And that's it for part A. Part B. When the height of the water is 3 feet, what is the rate of change of the water, of the height of the water with respect to time? Whoa, let me start over. When the height of the water is 3 feet is the rate of change of height of the water increasing or decreasing, okay? So let me go back. So we're still going to need, I erased it, whoops. We're still going to need this differential equation right here, okay? Actually, no. Just kidding. Let me start over. Okay, so they're asking us about the rate of change of the height of the water with respect to time. So remember, rate just means d over dt. The rate of what, right? The rate of the height. Okay, so we're wondering if this here is the rate of the change of the water increasing or decreasing. Is increasing or decreasing? This is what we want to know. Specifically when the height of the water is 3 feet. How do you know when dH over dt is increasing? So let me back up a little bit. We can tell if something will increase if what, right? So for instance, I know my function will increase if its derivative is positive, okay? So the only way I'm going to figure out if dH dt is increasing or decreasing is if its derivative is either positive or negative. So we have to go a little bit further here. So dH dt is negative 1 over 10 square root of h. So the second derivative would just be negative 1 over 10. Okay, let me back up a bit. This could be rewritten as negative 1 over 10 h to the 1/2, just to make things a little bit easier. So power rule would just be times 1/2 h to the negative 1/2 with respect to h. Okay, then you divide your differential by dt, and then you re-plug that back in. Okay, so here we go. We're going to have negative 1 over 20 h to the negative 1/2 times, well, what is dH dt originally? It was negative 1 over 10 square root of h. Okay? All right, so let's go a little bit further. If I multiply negative 1 over 20 times negative 1 over 10, I'll get positive 1 over 200. H to the negative 1/2 is really just 1 over the square root of h times the square root of h. So take a look at this here. This is my second derivative. Notice how the square root of h's cancel out, and you're left with 1 over 200 with no variable. So what does this really mean? This is saying that it doesn't matter what the height is, the second derivative will always be positive. Okay? So implying that what, right? So if I know the second derivative is positive, I know that dH over dt will increase. Okay? Watch that over and over if it didn't make sense, okay? Pause wherever you need to. Here's the last one. So at t equals 0 seconds, the height of the water is 5 feet. Use separation of variables to find an expression, okay? Okay, so here we go. They give us an initial value. We'll use that in a second. Keyword or phrase here is separation of variables. dH dt equals negative 1 over 10 h to the 1/2. Okay, so we're going to keep just a sidebar here. Usually if you have dy dx, the y's will stay on the left-hand side, the x's will stay on the right-hand side. So I want to make sure that h's stay on the left and t's stay on the right. I'm going to multiply both sides by dt. Okay, and I'm going to go ahead and bring h to the 1/2 over to the other side. All right, so this is going to give me dH and then 1 over h to the 1/2 or h to the negative 1/2. Okay, on the right side, I'm just going to have negative 1 over 10 dt. I separated my variables. After you separate, you integrate. So h to the negative 1/2, the integral will just be h to the 1/2 over 1/2 equals negative 1 over 10 t. Don't forget your constant. Okay? So right away, let me fix the left-hand side here. If you divide by 1/2, that's really just multiplying by its reciprocal 2. Okay? I am going to plug in my initial condition right away at t equals 0. H comes out to 5. Okay? So if you clean that up there, C will come out to 2 times 5 to the 1/2, or 2 rad 5, just to make it look a little bit cleaner. Okay? So here we go. We have 2 times h to the 1/2 equals negative 1/10 t plus 2 radical 5. Okay? So all you have to do now is get h by itself as simplest as possible. Okay? So I notice that there's a 2 here in the front. I'm going to divide by 2. So h to the 1/2 will now equal negative 1/10 t plus 2 rad 5 all over 2. Don't even make an effort to try to simplify that. Just write it out. It's safer, okay? So remember, h to the 1/2 is a square root. How do you get rid of a square root? You're going to square it. What you do to one side, you do to the other. So h will equal all that squared. Okay, equal is equal. Notice how it doesn't really match up with the scoring guidelines, simply because they simplified it a lot. Okay, so just keep that in mind.